we were discussing continuous time Fourier series and the different representation, and we have seen the three different representation of the Fourier series, and now we are deriving the relation between trigonometric and exponential Fourier series. We know I've already started with this in the previous lecture. The trigonometric Fourier series representation x of t is a0 plus summation n equal to 1 to infinity an cos and omega 0 t plus bn sin and omega 0 t. Cos and sin we can write in terms of e raised to form, as cos theta is e raised to j theta plus e raised to minus j theta by 2, and sin n omega 0 t is e raised to j n omega 0 t minus e raised to minus j n omega 0 t by 2j. And 1 by j is minus j, that is written in this step. Now if we consider this an terms and the bn terms, we can group the coefficients of e raised to j n omega 0 t and e raised to minus j n omega 0 t. And when we group the coefficient of e raised to j n omega 0 t, it is an minus j bn by 2 into e raised to j n omega 0 t plus an plus j bn by 2 into e raised to minus j n omega 0 t. Here plus j bn is this minus j bn minus. So minus minus we'll be getting plus here. Okay. Now assume xn is equal to an minus j bn by 2. And in the equation of this xn, we are substituting the expression for an and bn. An is, so 1 by 2 is taken outside. An is 2 by t integral 0 to t x of t cos and omega 0 t dt, and bn is 2 by t integral 0 to t x of t sin and omega 0 t dt. And from these two terms, 2 by t is a constant, so that is taken outside the integral 0 to t, taking 2 by t outside, 1 by 2 into 2 by t integral 0 to t x of t into cos and omega 0 t minus j sin and omega 0 t dt. And it is, see, this 2 and 2 cancels, and 1 by t is outside the integral, and cos theta minus j sin theta is nothing but e raised to minus j theta. So here we have xn is equal to 1 by t integral 0 to t x of t e raised to minus j in omega 0 t dt, and this is the expression for xn, which we have already seen. And in this equation, when we put n as 0, what we get is x0, which is equal to 1 by t integral 0 to t x of t dt, and that is equal to a0, which is the dc part in the trigonometric Fourier series. Again, so xn is equal to an minus j bn by 2. In this, replacing n by minus n, we have x of minus n, and in the right side the terms are going to be a of minus n minus j b minus n by 2. Now we know the expressions for an and bn. First, an is 2 by t integral 0 to t x of t into cos n omega 0 t dt. Replacing n by minus n, we have a minus n, which is equal to 2 by t integral 0 to t x of t cos minus n omega 0 t dt. And cos, we know cos of minus theta is cos theta itself. Therefore, this a minus n is equal to 2 by t integral 0 to t x of t cos n omega 0 t dt, which is equal to an itself. Therefore, we can say a minus n is equal to an, and that is an even Fourier series coefficient. And next, bn, expression is 2 by t integral 0 to t x of t sin and omega 0 t dt, and b minus n is, that is replacing n by minus n, it is 2 by t integral 0 to t x of t sin minus n omega 0 t dt. And we know sine of minus theta is minus sine theta. Therefore, this becomes minus 2 by t integral 0 to t x of t sin and omega 0 t dt, which is equal to minus bn. Therefore, we can write b minus n is equal to minus bn, and that is an odd Fourier series coefficient. So now substituting a minus n as an and b minus n as minus bn, in the expression of x of minus n, what we are getting is x minus n is an plus jbn divided by 2. Therefore, the equation of x of t, the original signal x of t in terms of xn can be written as x0 plus summation n equal to 1 to infinity xn e raised to jn omega 0 t plus x minus n into e raised to minus jn omega 0 t. This is where we have started with the trigonometric Fourier series. We have rearranged the equation, that is the terms an minus jbn in this equation. So this term is nothing but xn, and this we have got as x of minus n. Now we have this equation. Okay, now consider this equation here. So this term, here we have x minus n and e raised to minus j n omega 0 t. Therefore, this summation can be extended from n equal to minus infinity to minus 1 to include this term. Then it can be directly written as x of n plus e raised to j n omega 0 t. So by combining all the terms, we can write it as a single summation, that is summation x of t is summation n equal to minus infinity to infinity xn e raised to jn omega 0 t. Now this includes minus infinity to minus 1 will cover this term, that is x minus n e raised to minus jn omega 0 t, and when n is equal to 0 we get x0, and for n equal to 1 to infinity we get this term, this term xn e raised to jn omega 0 t. Okay, so from trigonometric Fourier series we can obtain the exponential Fourier series representation. So we can say exponential Fourier series is another way of representing trigonometric Fourier series, or vice versa. Okay, so next is line spectrum. Line spectrum means, see here we have seen the Fourier series representation of a continuous time signal. In that, in the Fourier series representation, we are representing the original signal in terms of harmonically related sinusoidal function. So for different frequencies, what is its magnitude? That relationship, that is line spectrum, that is a plot showing each of the harmonic amplitudes in the wave is called the line spectrum, and the magnitude spectrum is, see, modulus of x of n. We know x of n is an minus jbn by 2. Therefore, its magnitude is root of an square plus bn square by 2, and x minus n is an plus jbn by 2. We have already derived this earlier. Therefore, the magnitude of x of minus n is also root of an square plus bn square divided by 2, and this is equal to cn by 2, where cn is root of an square plus bn square. This we have derived. Cn is the coefficient in polar or cosine form representation. So we can say, therefore Cn is equal to 2 into modulus of x of n, 2 into modulus of x of n, and that is when n greater than or equal to 1, and it is x0 when n is equal to 0, because C0 is nothing but x0. x0 is a0, so C0 is a0 itself. And also the phase spectrum is angle of x of n. Angle of x of n is, we know x of n is an minus j bn by 2, and angle of a complex number is tan inverse. When the tan inverse imaginary part by real part, so that is tan inverse minus bn by an, and let this be equal to theta n. And similarly, angle of x of minus n is tan inverse minus b minus n by a minus n, and minus of b minus n is bn itself, and a minus n is an. Now this is minus tan inverse minus bn by an, and that is equal to minus theta n, which is minus of angle x of n. So we can say the phase spectrum is an odd function. That is, if you are asked to obtain the line spectrum, find modulus of x of n, and in terms of Cn, it is 2 into x of n, modulus of x of n, and you have to plot it versus the frequencies, different frequencies, and we will see this when we see the explanation for problems. Okay, so in the next lecture, we'll see the symmetry properties of Fourier series. Thank you.